In this video, we're going to discuss the enthalpy of formation. So we know that the enthalpy change is the name given to the amount of heat that is given off or absorbed from a chemical reaction or physical change that's carried out at constant pressure. And if this reaction is carried out under standard thermodynamic conditions, then we call it the standard enthalpy change. So for example, this particular chemical reaction, the combustion of propane, has a standard enthalpy change of negative 2043 kilojoules. So that's the amount of heat that's released from this particular reaction when it's carried out under standard conditions. So how are these standard enthalpy changes determined? Well, there's two general ways that we can determine how much heat is given off or absorbed from a chemical reaction. The first way is to perform that experiment, perform that reaction and measure the delta H value experimentally. This requires generally some type of calorimetry experiment. However, this is not always applicable. Sometimes it can be very difficult or expensive to carry out a reaction and measure its enthalpy change. So it's also possible to calculate the enthalpy change, the standard enthalpy change, mathematically without having to do an experiment. One way to determine the delta H of a reaction is to use the enthalpies of formations in order to calculate the delta H standard for that reaction. Now there's other ways, Hess's law, bond dissociation energies, but here we're going to look at using the enthalpies of formation to calculate the delta H standard for a chemical reaction. So first of all, what is the standard enthalpy of formation? And secondly, how can we use the standard enthalpies of formation to calculate the enthalpy change for a reaction? So those are the two questions we want to address in this video. The first thing we want to talk about is let's try to define what a standard enthalpy of formation is. So the standard enthalpy of formation has a fairly complicated definition. The standard enthalpy of formation is abbreviated as delta H standard with the subscript of F. And the standard enthalpy of formation of a substance is the enthalpy change for the formation of 1 mole of that substance in its standard state from its constituent elements in their standard states. Now that's a bit of a mouthful, but let's make some sense of that. Let's look at an example. Let's say we wanted to figure out what is the enthalpy of formation for CH4 or methane. Well, we would need to create 1 mole of methane from its constituent elements. So methane is made up of carbon and hydrogen. So to make 1 mole of methane from its constituent elements, this would be our chemical equation. 1 mole of carbon in its solid form, that's its most stable state, plus 2 moles of H2, hydrogen gas, that's the elemental form of hydrogen, would give us 1 mole of methane. So this would be the equation showing the standard enthalpy of formation of methane. Now, how much heat is absorbed or released when 1 mole of methane is formed from its constituent parts? Well, it turns out that the delta H of formation is negative 50.8 kilojoules per mole. Now, where did we get that value from? We'll talk about that in a minute. But let's practice writing a couple of equations real quick. Write an enthalpy of formation chemical equation, similar to what we did with methane, for each of the following molecules: carbon dioxide, water, and glucose. So pause the video and see if you can write a chemical equation showing the formation of 1 mole of each of these from their constituent elements in their standard states. Pause the video and give it a try. Okay, so let's start with carbon dioxide. So to form 1 mole of carbon dioxide is of course made up of carbon and oxygen. So we would have carbon solid plus O2 gas. Again, this has to be a balanced equation, which this is. For water, water is made up of hydrogen and oxygen. So to make 1 mole of water, we would take 1 mole of H2 gas. Again, this is what we call the elemental form of hydrogen. This is its most stable form. And a half mole of O2 gas. Now we have to have the half here because, again, it must be balanced, and we can't put anything other than a 1 in front of the water because by definition, the enthalpy of formation is the formation of 1 mole of a substance. And finally, for glucose, glucose is made up of carbon, hydrogen, and oxygen. So we need 6 carbons. We need 6 H2s, that would give us 12 hydrogens, and we need 3 O2s to give us 6 oxygens. So these equations represent the enthalpy of formations for carbon dioxide, water, and glucose. So where do we get these values from? Every substance, carbon dioxide, water in the liquid phase, glucose, solid, each of these substances has an enthalpy of formation value. How can we determine these values? Well, it's fairly simple. They've already been done for us. We just need to look at a table which has the delta H of formation for a variety of different substances. Here, this is a very small portion of a table, but if you look in the appendix of your textbook in the thermodynamic section, you'll see the delta H of formation for hundreds of different substances, and we can use those, as we'll see, to calculate delta H for any reaction. So our delta H's, we were looking for carbon dioxide, glucose, and water. Now the phase does matter. Water in the gas phase, water in the liquid phase have different delta H's of formation, so be sure to pay attention to the phase. So for each of our substances, we would just look on the table and we could figure out the delta H of formation value for each of these substances. One other thing that we need to note before we go on is that elements in their standard elemental state are assigned a delta H of formation of 0 kilojoules per mole. So for example, here's a list of a few substances in their naturally occurring most stable elemental form. Hydrogen exists as H2, oxygen is O2. So most gases, as you can see, are in the diatomic state. And so their delta H of formations are assigned a value of 0. Noble gases, just the monoatomic value, and things like metals would just be in their single elemental form, not combined with anything else. So pause the video for a second, take a look at the table, and be sure that if you see an element, you can recognize whether it is in its elemental form or not, so you know that it would have a delta H value, a formation of 0. So hopefully we've defined what standard enthalpy of formation is, but how can we use these standard enthalpies of formation to calculate the standard enthalpy change for a reaction, the delta H standard? And that's really where the standard enthalpies of formation becomes useful in calculating the delta H for a reaction. Well, we can use the enthalpies of formation of the products and reactants to calculate the enthalpy change for that reaction. So let's take a look at how we can do that. Again, this is really where the delta H of formation becomes important. So if I'm trying to calculate the enthalpy change for a reaction, I can take the enthalpies of formation of my products, which again, I can get those from my table, and I can subtract from that the enthalpies of formation of my reactants. Again, we could get those from a table. So let's say we had a reaction like this. A moles of A plus B moles of B reacts to form C moles of C and D moles of D. Our equation to calculate the enthalpy change using standard enthalpies of formation would look something like this. We would take the sum of our enthalpies of formation of my products. Now we have to multiply those enthalpies of formation times whatever coefficients we have here. Because remember, enthalpy of formation is the formation of 1 mole. So if we have a coefficient of 2 here, we would have to multiply the enthalpy of formation times 2 for that particular substance. So we would take the enthalpies of formation of my products times whatever molar coefficients are there, minus the enthalpies of formation of my reactants times their coefficients, if there are any. So hopefully you're not too confused. Let's take a look at an example. Let me work through an example for you and then show you that it's actually fairly easy to calculate the enthalpy change using these values. So let's say we were studying photosynthesis. This is the net chemical equation for photosynthesis. 6 carbon dioxides plus 6 waters yields 1 glucose plus 6 O2s. So what would be the standard enthalpy change for this reaction? Well, we can use the enthalpies of formation to calculate this. If we didn't, we'd have to do this experimentally, and it could be very tedious and time consuming. So first thing, let's set up our equation. The standard enthalpy change, that's what we want to calculate, is equal to the enthalpy of formation of my product. So glucose, the enthalpy of formation of glucose, plus 6 times the enthalpy of formation of O2 gas. Again, we have to pay attention to the coefficient, minus 6 times the enthalpy of formation of carbon dioxide, plus 6, again for water, 6 times the enthalpy of formation of water in the liquid phase. Now again, pay attention to the phases. So now all I have to do is look on my table and get the enthalpies of formation for each of these substances. So I can look on my table here. Again, this is the abbreviated table. Get the enthalpy of formation for glucose, carbon dioxide, and water. Now, notice that O2 is not on here. Remember, O2, that's the elemental form of oxygen, so the enthalpy of formation of O2 gas is assigned a value of 0. So now, here's my equation. I just plug in the values from my table. Again, I multiply them times the molar coefficients. And carefully, if I perform my math correctly, I should get the delta H value for this reaction should be about 2,756 kilojoules. So let's have you try one. Let's say you wanted to calculate the delta H for this particular reaction, and you needed to use the enthalpy of formations to do that. So see if you can do that. I'm going to give you this table here to look at. So pause the video and see if you can calculate the delta H value for this particular reaction using the enthalpies of formation from the table. Okay, so give the video a pause and see how you do. Okay. So for this particular reaction, I want to take the enthalpies of formation of my products minus the enthalpies of formation of my reactants. And we have to multiply times any coefficient. So our equation would look something like this: 2 times the enthalpy of formation of iron plus 3 times the enthalpy of formation of carbon dioxide gas minus 1 times the enthalpy of formation of iron 3 oxide plus 3 times the enthalpy of formation of carbon monoxide gas. Now, hopefully you recognize that iron, Fe, that's the elemental form, so its enthalpy of formation will be 0. The other values we get from our table, plug them in. Again, very carefully pay attention to your numbers, your units, your sig figs do matter. And if we calculate this correctly, we should get a standard enthalpy change for this reaction of 5.2 kilojoules. So we would say this reaction would be endothermic under these standard conditions. So please be sure you understand what enthalpy of formation is and how to calculate the enthalpy change, the standard enthalpy change for a reaction using the enthalpy of formation values.